Stanford University.
Hello? Hello? Yes. Welcome to EE380, Winter 2011-2012. I'm Andy Freeman. The other course organizer is Dennis Allison. It's getting to the time of the quarter when I remind students taking the class that it's good to keep up, no incompletes, all that fun stuff. I'm going to be especially brief today because nobody ever comes here to listen to me. Today's speaker, Stephen Wolfram, started his career in theoretical physics, and that's the last I'm going to say of that. Not because physics isn't interesting or cool, but Mathematica gave everyone an extra math degree, and that's pretty darn cool. And he's continued to improve our problem-solving and analytical capabilities. After that was fairly established, Dr. Wolfram went on to invent a new science, gave us a new way to discover and look and think about the world. That's also pretty cool. But more recently, he's launched Wolfram Alpha, which aims to make the online world actually computable and usable. And considering it's digital, that's really shouldn't have been a hard thing, but people just create crap data. So with that.
Great. Okay, well, I happen to be in the area which I haven't been for years, so I said I'll drop in and talk with you guys. So I thought I would be fairly informal here, and I'll say a few things, and then I'm hoping we can have interesting discussion, comments, questions, etc. And I had, maybe we can turn the lights down here so it's easier to see the screen. Maybe not, but anyway. I kind of had Wolfram Alpha sort of running through some paces here in the background to give an idea of the kinds of things it does. I don't know what the concept of Wolfram Alpha, and I'm going to talk about a variety of things here, but sort of the concept of Wolfram Alpha is something that at first seems a little bit crazy. It's try and take all this knowledge that our civilization has accumulated and try and make that knowledge computable, which means if there's a question that can be answered on the basis of that knowledge, make it possible to automate answering that question. So if there's some question where there's some expert somewhere who on the basis of knowledge that our civilization has accumulated could give you the answer to the question, try and set up a system that will automatically answer that question. So big, complicated project. Actually, I first started thinking about this project. We could probably you can switch the lights back on again if you want to, but you can. I started thinking about this project actually probably 35 years ago, maybe, and when I was a kid. And I thought this would be an interesting thing to do. I was kind of embarrassed recently. I discovered things that I did when I was like 12 years old, which were kind of the pre-Wolfram Alpha, but it was too early at that time. But I had thought, this would be a really interesting thing to do, but it's really hard. And so I had a variety of sort of conceptual reasons that I'd come up with for why this is too hard to do. So an example would be to do this kind of expert, making knowledge computable, answering questions like an expert and so on, would require, for example, making a whole artificial intelligence, like a human brain or something like this. And that's hard, I thought. Well, anyway, over the following 30-something years, every 10 years or so, I kind of looked again at the question of, okay, is it now possible to make something like this? And finally, I realized 7 or 8 years ago now that, yes, actually, I now think it might be possible. So what got me to that point was two big things that I'd done before, Mathematica and a new kind of science. And so the concept of Mathematica was a system that I started building 25 years ago last fall. So kind of the idea of Mathematica is to make doing technical computation sort of as automatic as possible. So sort of the concept is you should be able to all the sort of algorithms that people know about, you should have sort of an easy implementation of those algorithms. But more important, if what you know is that you need to solve a differential equation or lay out some network or something like this, then it should be possible to, let me just stop this because that's run out of interesting things to show. Let's just the concept is that that Mathematica should make it so that if you know the operation you want to perform, let's say it's solving a differential equation. Okay, that's even darker. Oops, that's not what I want either. Okay. Let me actually so the idea of Mathematica. You've got this operation you want to perform. The concept is automate as much of actually performing that as one can. So if you know what you want to do, have the computer figure out how it should be done. So for example, in solving some equation or some such other thing, there might be 100 different algorithms that could be used to solve that equation. The idea is to make it so that all you have to do is say, I want to solve this equation, and then Mathematica will figure out how to do it. Of course, you can have knobs and switches and things that you can set if you're a big expert in solving equations to tell it how you want it done. But in general, it's intended to be automated. The other big thing with Mathematica was sort of the original concept was, my original egotistical concept was, make a system that would do all the kinds of computations that I would ever want to do in my life, so to speak. So make it able to cover all kinds of different areas of computation. And to do that, one sort of had to make up some general framework for thinking about computation. And it ended up that the framework I developed was this idea of symbolic programming, which is a very general kind of framework that sort of has as its foundation the idea that everything that you have, whether it's a mathematical expression, a piece of graphics, a program, a document, whatever else, can be represented as a symbolic expression and can be represented in a very uniform kind of way. So this idea that everything can be represented as a symbolic expression lets one have a very coherent language built around that, where one has operations that can be performed sort of transparently across all those different kinds of things. And I mean, I suppose as a language designer, I ended up sort of thinking about things in kind of a similar way to the way one thinks about natural science. You know, there are all these computations that you want to do in the world. How do you break these computations down into sort of primitive elements that you can, from which they can all be built up? It's kind of like what you do in natural science. You know, you have the world around one, and how do you understand what the sort of underlying elements are from which all the stuff that we see around us can be built up? But so the concept is, in a computer language, is how do you find the right primitives that you can build everything up from in that language, and those are the primitives that become the functions that are given names in the language. And in Mathematica, we spent incredible amounts of effort trying to make this sort of very unified, consistent collection of underlying primitives that all sort of fit together in a nice, coherent way. And that's been fairly critical in actually building Mathematica as a system, because by now Mathematica is a big system. You know, it's got thousands of different functions in it and so on. And the fact that one sort of maintained a high degree of sort of design consistency and so on between these things has meant that these different building blocks can sort of fit together in very convenient ways. So I mean, I might as well just show you. Here, why don't we actually, since I'm talking about things with Mathematica, let's actually show you. So let's see, let's start with something. If we can't do that, we're in very bad shape. But okay, so let's say we say, you know, we ask Mathematica to plot a curve or something. Now we could go and we can say, let's say we say manipulate that, where I say, I put in a parameter here and I say manipulate this, this parameter runs from 1 to 10 or something. So now I'll get something which is, it'll just sort of automatically build me a little user interface where I can go and manipulate those pieces. Or I could make this, if I wanted to, I could make this, you know, a 3D graphic, I don't know, something like this, and then could say, you know, y goes from 0 to 2 or something, and now I'll have some nice 3D thing that that runs around, and we can turn it to different things if we want to. So kind of, and you know, this idea of this, you know, manipulate thing, you can apply that to anything. So if I had a polynomial that I'm factoring or something, and I say something like this, the same sort of manipulate thing can be applied to kind of any symbolic expression. So now I can just take my polynomial and be running around like that. Or let's say I have something else. Let's say I have a thing where I'm looking at I make some relation where I've got something like this: I goes to mod I squared comma 100. So that's a set of a mapping, so to speak. Well, so now in Mathematica we've got this sort of very automated way of taking that mapping and laying it out as an actual network graph. Or I could do something like this, where I combine these things and I say manipulate this with, instead of 100 there, let me put in a parameter n, and let me say manipulate that with n goes from, let's say, 2 to 100 in steps of 1 or something. And so now, oops, I forgot to tell it to make a plot. There we go. So now I can tell it plot these, and now as I change n, for each different value of n, it will be working out sort of the computational aesthetics of how to do a decent job of laying out the network that that I had. And you can go on doing this up to networks of size millions if you want to. So that's kind of another example of sort of how different pieces fit together. I might just say, you know, in terms of the way that Mathematica as a language works, you know, what are the sort of things that you can do? So let's say a typical sort of symbolic operation will be nest list. Okay, so nest list will do something like this, and we could nest anything we want. I mean, we could say nest, you know, the sort of the typesetting thing that puts frames around things, so then you'll get something like that. Or I could say, I could nest manipulate so that I get lots of different controls all nested. I don't know, we could say something like, how about this? Let's try, well, I can make up all sorts of things. Let's see what happens if I do something like this. See what weird thing this produces. Oh yeah, that's fun. So this is now a nested set of user interface controls. Unfortunately, they don't do anything very interesting here, but I could have hooked it up so they actually do something as well. That would take me another few seconds here. But it's kind of fun to see that you can take any of these objects and you can treat them symbolically and combine them together like this. Or another thing we might do is, let's say we take an image. Let's see if I can capture an image here. Let's see. See if this works. It may or may not. Well, it may not have got the right camera. Let's see. Nah. Well, let's go to the web and just capture a random. Let's go and capture some random image of something. How about that's a nice looking fish here. How about that guy? I don't know whether he's let's see. Will it let me copy it? I'm not sure. Let's see what happens. So that I can just. Oh, very good. Okay, there's our fish. It's a bit of an ugly looking fish, I'm sorry. But now we can use this fish as a piece of symbolic data, just like anything else. So we can just wrap a function around that. We can say edge detect that fish. And there we've now got an edge detected fish. Or we could say something like, oh, I don't know, let's say blur the fish, and now we could say, we give a parameter to the blur, some radius here, and now we could put one of those manipulates around it, and we could say, you know, manipulate that, a blur from 0 to 10 or something. And now we should have a little interface here, hopefully, where we can take that fish and make him less and less ugly. As, or we could, for example, we could take the fish here and we could say something like, you know, image partition that fish in images in size 20 or something. So now we should get, okay, so there's now the fish is broken into pieces, and now, for example, we could do something like, oh, I don't know, we could flatten that array, and we got a bunch of fish fragments, and now we could do something like we could sort those fish fragments by, what would you like to do? Let's see, we could take,
Blur them in parallel.
What's that?
Blur them in parallel.
What's that?
In parallel, you could blur them.
Yes, that would be fun. Okay, well, I'll tell you what, let's do this. How about, we could either blur them to a different extent, or I was thinking we could just do, we take image data from each one, and let's take the mean value of, let's just flatten it all out. Let's see what happens if we do this. And then let's apply that to this list of fish fragments here, see what happens. Okay, so those are now average RGB, average RGB values of all those things. So now let's say something like sort by, and then let's get our list of fish parts here, line 17. And then let's see what happens if we do this. So this should, if all works, yeah, okay, all right, that's actually fairly convincing. Okay, decent demo. So that's now sorted those fragments by overall color level. So anyway, this is sort of a quick introduction to one tiny corner of Mathematica. But It's also fun, you know, if I had got this camera working, we could have done the image processing in real time, which is always good to see. So you know, with Mathematica, we have the system that sort of our goal with it is basically implement every well-defined algorithm and make it so that there's a language that allows you to sort of construct those things into programs that do the things you want to do. And it's sort of, you know, our practical experience is if you have algorithmic software development to do, you would be crazy to use anything other than Mathematica because we just have more algorithms, more automated, sort of more connected together than anybody else has ever assembled. So one of the reasons I wanted to build Mathematica, as I mentioned earlier, is because I wanted to use it myself. And so one of the things that I've been interested in is sort of a general science problem. And let me explain a little bit about that because it's relevant to other things I want to talk about. So the general science problem is, how do you model things that happen in the world? So, you know, about 300 years ago, there was this sort of big idea that was to use mathematics and things like calculus to model things that happen in the world and to model, you know, motion of planets and comets and things like this. And that idea of using mathematical equations was a very successful idea that gave us lots of mathematical physics, lots of engineering, lots of other kinds of things. But the thing that I had kind of gotten interested in, 25 years ago now, more than that, 30 years ago, was what about systems where this sort of mathematical equations paradigm doesn't seem to work so well? And there are plenty of examples of that, even in physics, certainly in biology, certainly in lots of other areas of sort of human endeavor where this approach of finding a mathematical equation to describe things doesn't work so well. So the question is, is there a more general approach to making models of things? And if you're going to be able to make a model of something, then it has to be the case that at some level that the thing you're studying is governed by some kind of rules. The question is, what kind of primitives should you use for those rules? And should it be the case that the only primitives you can imagine using are things like mathematical equations and all these kind of constructs of mathematics that have been developed over the course of the last few hundred years, of, you know, exponentials and derivatives and all these kinds of things? Well, the thing that I got to thinking about is, what's the most general sort of category of thing that you can make models out of? And in sort of modern times, we have a nice kind of way of thinking about that, which is computer programs. And so then the question is, well, what if you just use arbitrary computer programs to make models of things? So that then leads one to a sort of general basic science question, which is, if you just imagine all possible computer programs, what do they typically do? And so this is sort of a basic science question. If you just started enumerating programs, starting with really, really simple programs and going up to more complicated programs, what kind of behavior would you see in those programs? And so this got me into the whole study of simple programs and what they do. And I guess my favorite type of simple programs are these things called cellular automata, and here's an example of one of them. This is just a cellular automaton that starts with a row of black cells at the top and then just evolves down the page. At each step, the color of each cell is determined by a simple rule. It just looks at the color of the cell above it and the cells to its left and right. And so, very simple rule. And not, one would think too surprisingly, the behavior is very simple. If we continue it for a while, we'll get that kind of pattern there. And that icon at the bottom shows the rule that's being used. You just take each triple of cells in each row, and you look at what they are, and you determine what the color of the next cell will be. So simple rule, simple behavior, exactly what one sort of might have intuitively expected. Well, if you keep going, and let's see. Fascinating. Okay. So here's another example. Slightly different rule. Again, simple rule, simple behavior, sort of what you expect. Well, keep going some more. Here's another example. Slightly more complicated behavior. And if you sort of run this particular thing longer, you'll find that you get this intricate kind of fractal pattern out. But still, you might have the kind of belief that if the rule is simple, the behavior must be perhaps intricate, but nevertheless at some level very, very regular. So that's a reasonable hypothesis, but the question is what's actually true. And so you can do an experiment. And so these days it's pretty easy to do an experiment about this in Mathematica. Let's actually start. that, and oops. So let's go and here. Okay, so we can make one of these cellular automaton things, and for example, can go and say something like this. We can tell it, make the cellular automaton, and now show us an array plot of the pixels in it, and there it is, and that's just one of those, that's one of the ones I just showed you. Well, now we can ask the question, what happens if you look at all possible rules of the general type that I'm talking about here? So what does the, what's the behavior then? So let's say we look at, there are 256 rules of the precise type that I was talking about before. Let's just make a table of the first 64 of those. So there's the result. And at the beginning, it looks pretty boring. You know, in each case, you're starting off with just one black cell, and you're asking what happens. So you keep going, you look through here. Mostly, you're seeing pretty boring things go on. It's kind of interesting that it's so diverse what the behavior is. You keep going. OK, there you might stop, because there is something more interesting. So this is the 30th one of these, rule 30. And what you see at first is something that looks considerably more complicated. So let's take a look at that particular one in a little bit more detail. Let's say we run it. Let's say we go ahead and run rule 30 for, let's say, I don't know, 400 steps or something. And again, this is starting off from just one black cell at the top and evolving down the page. And this is the kind of behavior, if I could make it a size where it's not aliasing too badly. This is the, I'll tell you what I'm going to do. I'm going to tell it to. OK, so this is quite a bizarre thing, because the rule is really, really simple. It's just one of these rules that says for every triple of pixels, you know, what color should you make? You're starting off from just one black cell, and you're getting this really complicated thing out. So to me, this to me was sort of is probably the most interesting science discovery I think I've ever made. And you know, you can see there's a certain amount of regularity in this pattern. You know, over on the left you can see there are periodic pieces and so on. There are triangles all over it and such like. But if you look, for example, at the center column of cells down the middle here, you'll discover, you know, when I first looked at this, I figured there would be some way to understand the simplicity of the rule on the basis of the behavior it produced. So I did all kinds of statistical tests and all sorts of other things on that center column of cells. And so far as any of those tests could tell, it was just completely random. And in fact, it turns out that center column of cells is random enough that it's a pretty good crypto system, and it's been used, for example, in Mathematica as a pseudorandom generator for the last 25 years and has been very successful at that. So it's kind of surprising that from something this simple, you can make something that has this amount of apparent complexity. Well, for me, this was something that's sort of pretty important in terms of understanding the natural world, because the natural world is full of complicated things. And actually, it's sort of an embarrassment these days that, you know, if you're shown something from nature, you're showing something that's been made by sort of human engineering, usually it's a good heuristic that the thing that looks simpler is the thing that we went to all that effort to make. And the thing that looks more complicated is the thing that nature somehow rather effortlessly made. And so it's sort of this question, what's the secret that nature uses to make all this seemingly very complicated stuff? And I think that this phenomenon is sort of key to what's going on there. And I think that what's sort of happening is that if you look at the space of all possible programs for making things, a great many of them show behavior like this, where you get very complicated behavior even though the program is simple. And that's kind of what nature is ending up using to make all the sort of complicated stuff that it makes. And so I got, with that general idea, it's kind of an intuition-breaking idea because we usually think, if we're doing engineering, that you have to go to a lot of effort to make something complicated. But what we're seeing here is that even just these programs sort of picked at random from this sort of computational universe of possible programs will often produce stuff that is very complicated. So that's, that sort of observation got me started on trying to understand all the different areas of science that could be affected by this change of intuition of realizing that just these simple programs out in the computational universe can do complicated things. And there are all kinds of things that you can study in physics, about the fundamental theory of physics, in biology, about how biological form gets made, and sort of ways to think about how biological processes and biomedical kinds of things work. even in pure mathematics, understanding things about sort of what mathematical theories have been investigated, but what ones are out there still to be investigated, and how we've kind of chosen the ones that we've chosen. And there are lots of kind of general principles that emerged from studying this kind of thing. But one example is, well, there's a big one which I call the principle of computational equivalence. So you could ask the question, sort of, how do you think about behavior like this? And you can kind of think about any of these processes as being some kind of computation, where you start off from some initial condition, then you compute, and get some behavior out. And the question then is, you look at different kinds of systems, how do the computations that they perform compare? And you might have imagined that if you had a very simple system, it would do very simple computations. As you make the system more complicated, the computations would get more and more complicated. What this principle of computational equivalence says is that actually that isn't true, that instead after you get above some very low threshold, the kind of computations that these systems do are all equivalent. So that principle has all kinds of predictions. Like it says, if that's the case, then if you just sample programs at random, any one that isn't sort of obviously simple should, for example, be capable of universal computation. And we know, for example, that one of the ones, we don't know about this particular one, Rule 30, unfortunately, yet. But we know, for instance, that, let's see, this guy, this is Rule 110. We know that this particular very simple cellular automaton is capable of universal computation. And for example, among Turing machines, I was curious, what's the simplest universal Turing machine? And so I looked at all Turing machines, starting with the simplest ones. And there's a Turing machine with just two states and 3 colors. And that Turing machine, according to this principle of computational equivalence, one would expect that that Turing machine, which is sort of the first one that isn't obviously simple, would be capable of universal computation. And indeed, we ran a little competition a few years ago, and somebody proved that, yes, indeed, that particular Turing machine is capable of universal computation. So that was a nice piece of evidence for this principle of computational equivalence. Well, the principle of computational equivalence has all kinds of consequences. So an example of a consequence is the idea of computational irreducibility. So one can ask the question, if you look at a pattern like this, can you figure out what's going to happen? Can you make a prediction about what's going to happen here? And sort of making predictions is one of the kind of hallmarks of successful exact science, or so one's taught. But in this case, it's very straightforward to just run the rule and find out what happens. What this principle of computational equivalence implies is that there can be a certain kind of computational irreducibility. See, we usually assume that we're, in a sense, much smarter than every system we study. So, even though it may take the Earth, 1 million years, some idealized planet, 1 million years to go around its star 1 million times, we say, well, we don't have to wait for, we don't have to trace all those 1 million steps. We can just use some clever mathematical equation and jump forward and see the answer. So we're kind of using the fact that there's a kind of computational reducibility, which is the result of sort of us being smarter than the systems we're studying. But this principle of computational equivalence says that that shouldn't be the case. That in fact, our brains, our mathematical techniques, all these kinds of things should just be equivalent in computational sophistication to even these really simple systems that we're studying. So that means that we won't be able to win that competition systematically, and we'll be sort of stuck having to kind of trace through, having to go to as much computational effort to find out what happens as the systems themselves have to. So that's that idea of computational irreducibility. It has all kinds of consequences. It kind of tells you things about why things like simulation are not only convenient, but actually in some fundamental sense necessary when we study all sorts of systems. There are all kinds of consequences. Well, this principle of computational equivalence has all kinds of consequences too. Like it tells one things about thinking about, one area that's important is thinking about things like intelligence. You might have said, well, gosh, there must be this big dividing line between the intelligent stuff out there and the non-intelligent stuff out there. And that's what I kind of always believed, was that there was this sort of, you could discover these clever inventions that would lead you to these sort of intelligent AI-ish things, and that was different from all the other sort of just computing things that one could do. But I kind of realized, you already realize, you think about, what's the definition of life, for example. Very easy historical definition of life on Earth, because all life on Earth is kind of derived from the same lineage of, has the same RNA and cell membranes and who knows what else. But if you try and define life abstractly, it's quite difficult. You say, well, the Greeks said, if it can move itself, then it's alive. Clearly not a good definition. If it can reproduce itself, then it's alive. Again, not a good definition, and so on. So what you realize is that there isn't really an abstract definition. It's just defined historically. And I think the same thing is true for intelligence. And that's a relevant thing because it sort of tells one that there's no sort of bright line between the intelligent thing and the thing like this. And so, if we get the signals from the extraterrestrials or something, and they're producing all these complicated patterns and so on, we might say, wow, this must be an intelligent thing that made all these complicated patterns. But no, actually, it could be some very simple rule like this that some simple physical process might be responsible for. So it's kind of evidence that this idea of sort of this bright line of intelligence isn't really there. Well, so there are all kinds of things about this kind of science. I'll just mention a few, and I'll come back to this point about intelligence. So in terms of this kind of science, one of the interesting meta things one realizes is that it gives one a new way to do engineering. It gives one a new way to do science because it gives one sort of a lot of new raw material for making models of things. We previously were saying we want to make a model, we'll write down a differential equation, we'll do this or that. Now we've got this whole raft of new kinds of models that we can use, and indeed people have used things like Cellular Automata and other kinds of sort of computation type models to study all kinds of systems. I kind of had a joke at one point. There are 256 so-called elementary cellular automaton rules. I first started talking about these in the early 1980s, and they're all numbered, right? And so I used to have, in the days when one had file cabinets, I used to have this file cabinet where I had a file folder for every one of the elementary cellular automaton rules. And gradually, and when papers would come in about different applications of cellular automata, I filed them according to which rule they were. And I thought, like there was Rule 90 papers that were talking about some mathematics and some things about, models for catalysts. And then there was, Rule 184, which turns out to be a good model for road traffic flow and traffic jams and things. And then eventually there were things like Rule 4. I remember the day when I got the paper about Rule 4. I said, nobody will ever do anything with Rule 4. It is a completely boring and uninteresting rule. But then it turned out there was some signal processing algorithm that got invented that was based on that particular rule. It was kind of interesting to see in the space of possible rules how sort of the applications of these things filled in, and there was this kind of lumpy distribution of some were more important than others and so on. But but in any case, for science you can go. That is a bad sign. Why did that happen? Oh, it came back. For science, you can go and sort of sample this computational universe of possible programs. I suppose the ultimate thing like that one can do is try and find a fundamental theory for the universe this way. That will get me off onto a huge sidetrack. I'd be happy to talk about that if people are interested in it. But basically the question is sort of our physical universe a rule that exists in this computational universe of possible universes? And it's been my kind of hobby project for a long time to try and figure this out. And there's lots of interesting things to say about deriving all sorts of properties of space-time and so on from much more primitive things that lie sort of underneath space and time and so on. But that's sort of a separate topic. The other thing beyond science that comes out of studying these kinds of things is things for engineering. And often in engineering, what we're used to is we say we want to engineer some particular thing. We want to create something for some particular purpose. Well, we get some human engineer to try and figure out how to do that. There's an alternative approach, which is essentially algorithm discovery, program discovery. You just say, we've got this particular objective that we have. Let's just go and exhaustively search the computational universe and try and find a program that that satisfies the objective we have. Now, you might have said that's just completely crazy because, if you're just enumerating programs, you'll never find one that's rich enough to be useful. But that's what we discover from this sort of new intuition isn't true. That actually you can find programs that are useful and interesting, not very far away in the sort of the space of possible programs. And so, for example, this is a technique that we've used a lot in building Mathematica and even more in building Wolfram Alpha. So I mentioned, like this particular thing is a really good pseudo-random generator. There are other rules that are really good for making hash codes. There are other ones that are good for image processing. There are other ones that are good for doing Fourier transforms. There are other ones that are good for other kinds of things. What's interesting is you go and you search in this sort of computational universe of possible programs, and you find all this stuff. And you often find these things which are, you look at them and you say, I don't understand how this works. You can prove that it works. but it's something very alien. It's something no human would ever have come up with. But nevertheless, it may be the most efficient instance of something, or even the only easy-to-find instance of a thing. And it's interesting, when you see algorithms that are like, iteration, when you see something that's sort of doing iteration, it has this very simple periodic structure. You see something that's doing recursion, it tends to have this very simple nested structure. And then, you can have other sort of quite different ways to achieve operations, and there are things that kind of visually look vastly different. I think I might have an example. Here's an example of just some cases of these are just cellular automata that achieve the objective of doubling the size of their input. And what's interesting is some of them achieve that objective in very simple sort of engineering-like ways. Some of them achieve that objective in very elaborate, ornate things that don't look like they would ever have been produced by a human. In this particular case, the most efficient one is actually something fairly simple, but that's often not the case. So in any case, one of the things that came out of NKS is this sort of idea that you can sort of search the computational universe for useful programs that do things, and not only programs, also, if you're doing nanotechnology or something and you're trying to find the universal constructor or something like this. One approach might be, well, you take something that does that at a large scale and you shrink it down, you make it very, very small. An alternative approach is to say, let's just search. We know what components we have. Let's just search for how we can combine these components to make something that achieves the objectives we want. And that's the kind of approach that you're led to by this kind of thinking. Well, okay, so having said all of that, one might wonder, perhaps, I don't know, so I worked on this kind of science for a long time, worked on Mathematica. I was interested in doing, sort of making knowledge computable and so on, and how did that sort of lead to the idea that Wolfram alpha might be possible? Well, the main conceptual thing, as far as I'm concerned, was this realization from the principle of computational equivalence that there's sort of nothing that special about intelligence and things like intelligence, and it's all sort of just computation at some level. And that kind of was, for me, that little sort of philosophical realization was, for me, kind of the launching point for thinking, gosh, it might actually be possible to take all this knowledge that exists in the world and make it computable. So let's see, I mean, the result of all this, I can show you, you probably, I hope you've seen, I think by now, among, let's say, US college students, there is a remarkable, the number of, the fraction that seem to use Wolfram alpha regularly is remarkably high. So, I mean, basically, sort of the idea of Wolfram alpha is, you type in some query, and Wolfram alpha tries to tell you something interesting about that query. So it'll, you type in x sine x, it'll show you some plots, it'll work out some things about that. You might say, instead here, you might say, what is the integral of x sine x? And it'll go and try and work out the answer, and then it'll try and sort of tell you interesting things about that answer, and this network connection is really slow. But what's, I mean, the sort of the idea of Wolfram alpha, it can do this across all kinds of domains of knowledge. So, if you say something like, GDP of France or something, it can go and tell you what the answer is and give you a plot, or you can say something like, what is the GDP of France divided by Italy or something like that, and it will figure out what that means and give you a plot of the result. Hopefully it's really slow here, but there it is. And or we could say something like, I don't know, we could type in, something like this, and we could, and it'll probably figure out that that's a base pair sequence, or that we probably mean that to be a base pair sequence, and then it'll go and figure out, oh, there are no exact matches for that on the human genome. Let's cut some letters out here. It'll go and try and figure out what exact matches there are on the human genome, for example, to that particular thing. So in this case, we've got a bunch of matches on a bunch of random chromosomes. We could go and ask it what it knows about one of those genes if we care. We could go and figure out things like this, or we could ask it something like, how about, I can ask it, let's see, yes, this won't be, actually the real thing I want to do, if I stop using, well, I have a choice here. I'm using VPN, so this thinks it's somewhere in Illinois right now, which means that it isn't quite as interesting to type weather, because it's always fun when you're writing software and you can do something where you can just look out of the window and find out if your software is working correctly or not. But we can say, well, how about we just say weather Stanford? See what it figures out there. Oh, okay. Current weather, assuming Stanford is a university. Okay, current weather for Stanford University. There it is. Okay, so that's the history for the last few days. That's let's say the past 10 years or something of weather. There was a prediction there as well. Okay, so there's the weather for the past 10 days, 10 years, and so on. Or we could, for example, we can say, let's try this. Let's try planes overhead. That's another. Let's see whether I can figure that out. Okay, flights seen from Stanford University. Okay, so these should be planes that if we went outside we could go and look and see that they're all very close to the horizon actually. Let's try and look at this one, for example, some random plane at 33,000 feet right now. Oh, no data available. That's surprising. Oh, maybe that is surprising. Usually when the plane is high up, it's been flying for a while, and you can. Let's try one other. And that one might. Okay, so this one it seems to know something about. So it's a plane going from somewhere to somewhere, and it's always kind of interesting to me how much quantitative stuff there is to figure out in the world. So this is a plane, and it's there's its location, and you can see the little circle showing what the region where it can see that plane or that can be seen from the plane. There's its altitude. Okay, it's an Airbus. It looks like it's just climbing because that's its altitude as a function of time. And there's okay, it's heading. It's made a few turns, and there's some cities nearby, and so on and so on and so on. Yes. Is
there some sort of algorithm discovery in order to get to these results right now going on?
What do you mean by that?
So what are the steps that you follow in your data center in order to produce these results right now?
Okay, so to explain that, I have to sort of explain the whole idea of what's going on. Okay, so let me. Okay, that's good. Thank you for asking that question. Let me. So, kind of the flow in Wolfram Alpha is free-form natural language input gets turned into some precise symbolic expression that is sort of a precise representation of what we think that query probably meant. And then we compute what we can compute from that. So there are basically four big pieces to building Wolfram Alpha. One thing is there's lots of underlying data. Where does the data come from? The data is not foraged from the web. Essentially, none of it is foraged from the web at this point. Almost none of it is foraged from the web. That turned out to be a messy problem, sort of fraught with all kinds of issues and not very reliable. So the first step is just go get data across all these different domains, thousands of domains, and you get this sort of very systematic data. By now, the number of terabytes of data, raw data that we have is quite big compared to, for example, the textual content of the web. And so, for example, for airplanes, that data, well, this particular thing is a feed, right, coming from the FAA, and it comes in, I think it's a couple of megabytes a minute. And we've obviously got the archive of this feed going back as long as we can go back. And actually for airplanes, it's kind of an interesting thing because just having the raw data is only a small part of the problem, right? You have to go from this raw data to something that's actually computable. So in the case of airplanes, the FAA feed is delayed by some number of minutes. So if you actually want to figure out what planes are overhead, you have to, continue the trajectories forwards. You have to project forwards for some amount of time and then do all the various geocalculations to figure out what you can see and so on. So that's sort of a typical case of where there's a blob of raw data, but to actually answer questions from that raw data, you have to make the data computable. And we've ended up with this kind of rather elaborate pipeline for sort of going from the raw data, sort of being able to understand the raw data, validate the raw data. It helps to have thousands of domains already done because that makes it easier to see whether the 1,001st domain's data is sensible or not. And then going from that, trying to, what we found is that we typically always have to have sort of experts in the loop. If we actually want to get the right answers from this data, we always have to actually and conveniently because of life and times with Mathematica and so on, we typically have sort of easy access to the world expert in some particular area. And usually it's a great conversation. It's like, can we talk to you for half an hour about your field because we want to make it more accessible to lots of people? And it's like, when I have a chance, I get on some of those phone calls because they're always pretty interesting. But anyway, so you have to kind of inject some expert knowledge into the whole thing. And then, so, one step is sort of take this data, sort of organize it to make it computable. Another step is actually implement all sorts of methods and models and algorithms and things that go from that underlying data, or in some cases, the things one's going, they may not go from underlying data. I mean, like, for example, if I were to, oops, what did I just do? Okay, if I were to just, type in some random number here, right? I mean, Wolfram Alpha will probably go and try and figure out what might this number be, right? So that's not, so it could be, that number could be some strange multiple of pi, or it could be some other strange thing. These are things which are kind of algorithmic things that don't start from any kind of raw data as such. They're just computations. It's always interesting to see, if you have some kind of thing like this. 567 ohms, right? Well, so you can do things like you can do some unit conversions. You can do things like this. You can say, how does that compare to standard resistors? Okay, you can't make that out of standard resistors, but then, okay, you can do a computation. You can figure out what combination of standard resistors will get closest to being able to make that particular result. So this is, these are, again, typical examples of where the raw data is, here's the collection of standard resistors, things like that. But that's not that useful as such. What's useful is to be able to compute something like, here's how to make a particular resistance you type in out of standard resistors. So there's this, a big part of the Wolfram Alpha project is to implement all these methods and models and algorithms and so on. And now the whole of Wolfram Alpha is about 15 million lines of Mathematica code, of which a big chunk is implementing sort of all those things that have been figured out in science and engineering and financial analysis and who knows what else, actually implement those algorithms. So that's sort of another big chunk. Another big chunk is, okay, so you can compute all this stuff, all this data. So now the question is, how do humans communicate with it? Well, the only option is to use natural language because it's too diverse an area. You can't build a formal language and expect people to know how to interact with it. So then the problem is, well, can you let people just type in natural language and have it be understood? And I thought this might be just plain impossible. I had all kinds of arguments for why it might be too ambiguous and you might never be able to decode it and so on. But we decided to just start trying to do it and use a bunch of methods from NKS and so on to try to make that work. It turned out to be, well, I think we figured out a lot of new things, because what we've ended up doing is very different from either sort of the text retrieval model, the text retrieval search engine type model of matching sort of queries with existing text. It's also very different from the parsing of full sort of full sentences that you get in typical kind of natural language parsing and so on. I mean, it turns out it's kind of interesting. We can now see billions of actual queries that people type into Wolfram Alpha, and I kind of have this meta theory that what we see is this. It's a strange pseudo language, which is a combination of kind of. I think it's actually fairly close to people's underlying thought processes. I mean, in the sense that they're little fragments of grammatical stuff all combined together. Just, they thought they were doing this, and then they thought of something different, and there we see the result, and it comes in. So, so another big piece is to actually do that natural language processing, do the kind of language understanding. Our kind of goal in doing that is something probably much crazier than most people have ever tried to do before, which is that we absolutely want to nail what the person meant. And sometimes we don't know for sure. I mean, if I type in, if I type in some random word, let's say I type in, Springfield, right? We know there are multiple possible cities, multiple meanings for that. So we have to decide, which one are we talking about? Well, it turns out, because we have certain knowledge of the world, we can disambiguate that with very high probability. So for example, this thought I was in Illinois, so it guessed that I probably meant Springfield, Illinois, but it knows where I am, it knows where these cities are, it knows what the populations of these cities are, it knows kind of how famous the cities are according to how much they're talked about in Wikipedia and things like this. And it combines all those things together to try and guess which thing we actually meant. And so actually one of the things that we end up doing in Wolfram Alpha, it's sort of interesting in a way, is that for every query that comes in, we actually say, we're going to guess, we're going to say, we can say what the exact thing that query meant was. Different objective than, it's sort of and what's somewhat surprising to me is that works a very large fraction of the time. That is, people had a definite idea, and we can figure out what it was, and then we can go compute things from that idea. Now, obviously, there are so that's kind of that's another component of what we're doing. Another thing, so beyond sort of the data, the algorithms, the language understanding, another big component is, well, what do you actually produce as output? Right? You can compute all kinds of things. What do you actually produce? So, for Springfield, what do you actually tell people about Springfield? And you might say someplace down here, I bet it's going to say, yeah, notable people born in Springfield. Okay, that's about the only thing I know about Springfield, Illinois. So this idea, but the sort of meta idea here is, given some query, automatically generate a report about what the world has to say about that query. And that's kind of the notion. I suppose it's interesting maybe to compare what we're trying to do with computational knowledge with, for example, the world of search engines and things like that. I mean, what we end up trying to do is to say, search engine, there's this big web out there of, probably, I don't know, 10 billion pretty interesting pages and some number of 50 billion not so interesting pages, and, lots more of other random stuff. And the question is, given the bag of words that you type in, is there a match to that bag of words somewhere on the web? And so that's what one tries to do there. And sort of and so if you have some question, if the answer to that question has been explicitly written down somewhere before on the web, you can pick it out by that kind of searching text retrieval type thing. If the answer to your particular question has never been written down on the web, then you're out of luck by that technique. And what we're trying to do is to see, well, when can we actually answer questions by computing the answer rather than by looking up the answer. And the other thing we end up doing is, because we actually can get a definite interpretation of a query, we're able to say, from that definite interpretation, let's just generate a report about what we have to say about that interpretation. We're not saying, it turns out that we can sort of take a different path from the path of saying, here are a bunch of possible things you might want to look at based on the query. It's kind of like, I suppose at some level, it's like the, you go to a library and you say, I'd like to know about something, and somebody can say, well, here are 10 books you might want to read about this. The sort of alternative is, here's some report that somebody, some analyst has made that tells you specifically about the particular question you asked. And we've been trying to do this sort of, in a sense, much crazier thing of trying to actually answer specific questions that people ask. It's kind of interesting. If you look at our query stream now, the percentage of queries that we get whose literal form exists somewhere in the web is dwindling at this point. And that's partly because the queries have actual numbers in them and people ask specific questions. And the other thing that's very encouraging is that the fraction of queries that we can understand is now very high. Now, it's partly because people have learnt what Wolfram Alpha can do, but it's also because we've been gradually learning from what humans have sort of thrown at it. Well, okay, so I mean, the whole thing is a pretty complicated system, and I'm always continually surprised that it actually works as well as it does, because it's a very big thing, and it involves lots of different pieces, which are, any one of which could be horribly fraught with difficulty. But maybe I could show you a little bit about what sort of the future of this kind of thing might look like, but I'm not sure. I think I've almost run out of time. I've been yakking for ages here. Maybe I'll show you if people. I'll show you a few things we're playing with. So here's an example of something we're playing with. So Wolfram Alpha, as it is configured right now, is mostly about taking things like text as input. So you can also do things like, for example, you could take an image as input. This is just something we're playing with, So, you know, there's an image, and now sort of the default thing would be to compute a few particular things about that image. And actually, it's fun. You can combine kind of this thing called CDF, the computable document format, which is something derived from Mathematica language technology. Combine that with Wolfram Alpha, and here we're sort of on the fly generating some piece of interactive code that we can then run, in this case, to do some simple piece of image processing. But you know, I could say here, well, let's say I just want to do something like edge detect this particular image up here, and then it'll probably go and be able to do edge detection on it. And it's actually interesting, you know, you can do this kind of natural language type. Let's see, I've got a Mathematica here. Yeah, you can do this kind of natural language version. So like in Mathematica, it's kind of interesting. You can type into Mathematica. You can type kind of free-form input that then uses Wolfram Alpha to go and be able to sort of generate precise programs there. So we can take that. We can say something like, let's see what happens if I say rotate 30 degrees. Let's see if that works. I don't know if this will work. Oh, it just gave me the rotation matrix because I should have said rotate the image 30 degrees. Maybe I could say, let's see what happens if I say blur the image, see if it figures out which image I'm talking about. May or may not. First of all, it has to actually, no, it didn't manage to figure it out. Okay, well, maybe I can say, let's say draw a green circle. But in each case, what it's doing is it's generating the actual, it's generating the actual Mathematica code that's necessary to do all these things. And it's kind of interesting to see how you can combine kind of free-form linguistics with that actual, with that sort of precision of a programming language. Well, another thing you can do that we're sort of playing with is being able to not only give Wolfram Alpha as input something that's a pure sort of query that relates to sort of public knowledge in the world, but you can also do something like upload a bunch of data that you've created or something to it, and then say to it, okay, go analyze that data on the basis of what else you know. So this is an example where, let's see, we can probably look for the original data. Okay, so this is just some random blob of structured data, or somewhat structured data. And so then we can go back, and in this case, we just sort of threw that data at Wolfram Alpha and said, okay, what can you figure out from that? And so it will then try and work out, you know, what might be interesting to give us a sort of a report based on that data. And so there's a few examples. Maybe there's some statistics. It's worked out some statistical things. Maybe at the bottom, it came to various statistical conclusions based on doing some regression analysis, something like that. Or you can go and say, I don't know if I've got an example here which shows this. Let's see. Let's try, how about this? Let's try that. So here we've got just another example of some random data, but now this data had, in this particular case, it had, I think, names of countries in it. Okay, so we could recognize what, you know, we have all this linguistics, so we can figure out what this sort of actual country that was being referred to was. In this case, it makes various raw data plots, and probably somewhere down here it'll make some heat map plot, which has recognized that those are, you know, names of countries, and you can go and do this, and you know, the fact that you can kind of show off and see that it actually really knew that those were countries, and it knew things about those countries. So instead of just plotting the original data, we can say normalize it by population, because it obviously knows these are countries and it knows features of those countries and so on. So this is kind of one of many kind of frontiers of things that we're doing, that being able to take kind of data from the outside world and combine it with data sort of from data that one uploads, and sort of combine that with knowledge that we have of the world and try and deduce interesting things from it. There's a lot of other stuff that well, I can talk about lots of different things that we're trying to do. But I said I would kind of just talk for a bit and then get questions and comments and so on. So I think I've been talking for too long. So probably I should stop, and we should sort of open this up for questions, comments, whatever else. Yes, please. Yes.
On that center column on your pyramid,
yes.
I guess it was random black and white sequence.
Yes.
But on the side, it looked regular. So each time you do it, you get a different
Oh no, 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 no. It's just you're following that rule at the bottom there, and every time you do this, you're going to get the exact same. I don't know what that did, but that's really weird. Okay, it could be dangerous to press that. No, it didn't seem too dangerous. Every time you do this, there's no probabilities involved. Every time you do it, you get this precise same thing. It's like computing the digits of pi or something. There's a definite algorithm. There's a definite sequence. It just so happens that that sequence, like the digits of pi, even though it's definite to produce, is seemingly quite random. And so, for example, there are now, there's a whole literature tree of papers about all the regularities on the left-hand side of this pattern now. And so quite a bit is known about it. Unfortunately, I've been hoping, I'm trying to predict how many years it will be before somebody proves anything about the center column. It's so far there is nothing that's been proved about the center column, but it has been proved that the 1 plus epsilonth center column, in other words, one center column plus epsilon of another column, doesn't repeat. So that's as far as it's got. It's not down to even that the center column doesn't repeat, although I'm sure it doesn't. But yes, this is and the fact that you can see some irregularity here is not it's not surprising because there is an underlying definite rule. But what's interesting is that so much of what one sees has such complexity to it. Yeah.
That the center column, it's expensive to compute because you have to keep one row. I mean, your intermediate storage is growing linearly with the.
Yeah, if you wanted to compute, so for example, when we use it as a pseudorandom generator, we're just using it in a fixed size register. So actually, okay, so to fill in that story a little bit more, because it's slightly interesting. So we used Rule 30 as a pseudorandom generator, default pseudorandom generator in Mathematica for many, many years. And then we said, surely there's a slightly better cellular automaton out there. So then we actually, because this was one, it's just too easy to use this one, so to speak. So then we actually did a big search of trillions of these things, and we found some that are slightly better, in the sense that you can use smaller registers, and you can have things, and you can also do nice sort of clever. They're particularly nice with respect to parallel bit operations and computer words and so on. So we don't actually the version starting with version 8 of Mathematica, the absolute default pseudorandom generator isn't precise to Rule 30. It's another more elaborate cellular automaton.
Well, it's more interesting. You said you limited the register size. I would have expected the theories to be qualitatively different between on the integers this way and on a fixed register.
No, it's not qualitatively different. You can work out things like what's the period length and so on, and we know a lot about what the period length is. It's not a maximal length sequence. It's about 2 to the 0.6 n. And if it were a maximal length sequence, that almost implies certain kinds of regularity, and that's why in like linear feedback shift registers, which do have maximal length sequences, that sort of implies a certain algebraic structure and a certain regularity to the whole thing that that this would have too if it was a truly maximal length sequence. But yes, there's now in terms of it is true that the theory is different for a smaller register. Yeah, right. So, I forget what the actual boundary conditions are that we use in the final thing that's used in Mathematica. The simplest thing to do is just wrap it around in a cylinder, but you can do other things as well. Yeah, okay, that's it. Okay.
Stephen, can you say something about how Seth Lloyd's work on programming in the universe compares with what you're doing?
No. I have no idea. I have no idea what Seth has been up to recently. So.
How about just a more general version of that question? You said there's a whole sidetrack that goes down into theoretical physics, cosmology, and digital.
Okay, so I can talk a little bit about that.
So go down that sidetrack for a few minutes.
Yeah. So the question, the meta question is, if you think about this computational universe of possible universes, is our physical universe easy to find there? Might not be. It could be that our physical universe, there is a program for our physical universe, but that program is incredibly huge, right? So it could be that in a sense, if you think Copernicanly, so to speak, you would say there can't be anything special about our universe. It must just be an arbitrary universe in the space of all possible universes, just like our star is an arbitrary star in the in the 100 billion stars and the 100 billion galaxies and so on. So but nevertheless, it's a reasonable thing to ask. So one meta fact we know in science, which is that our universe is not as complicated as it could be. And this is sort of a basic fact that was noticed by theologians a long time ago, and it's sort of the basis for science in a sense, which is, there are maybe 10 to the 80th, 10 to the 90th particles in the universe, and every one of those particles could be doing a different thing. It could have a different rule, there could be no regularity whatsoever. But we know that that isn't the case. So we know that the rule for the universe is quite small compared to sort of the universe itself. Now the question is, how small? Is it a rule that, if you wrote it in Mathematica, would be 5 long, 5,000 lines long, 1,000,000 lines long? How long is the rule? So it seems like a reasonable thing to at least ask the question, what about, could it be a simple rule? And you can just start enumerating rules, and you can see, could this be our universe? Could this not be our universe? Well, when you start doing that, you have to think a little bit more about, what will be the raw material? What kinds of rules should you look at? Well, the thing you realize is, if there's a very small rule for our universe, then essentially nothing that's familiar to us about the universe can be encoded directly in that rule. There simply isn't room. I mean, if you've only got 3 lines of code, you don't get to put a 3 in there for the number of dimensions of space, and you don't get to put a 206 for the mass ratio of the muon and the electron and so on, right? It has to all emerge from what's there. So then the question is, what might be in those 3 lines of code or whatever? And so you have to look for what's the lowest level thing that's sort of below space and time and particles and all those kinds of things. I think what's interesting is when you're at that lower level, there are many equivalent formulations. But one that I happen to have found convenient and studied quite a bit is to think about sort of the whole universe like a network. So the idea is that all there is ultimately is a bunch of nodes and connectivity of those nodes. That's it. There's nothing else. And so how do things emerge from that? Well, it's just like, you have a fluid like water at a low, it seems like a continuous thing, but at a sufficiently low level, it's made of a bunch of molecules bouncing around. And so that's how space might work too, that at a large scale, it seems continuous, but at a small scale, it's like it just has a bunch of discrete nodes. And, it's not hard to see how you can arrange those discrete nodes to be like, a one-dimensional thing, a two-dimensional thing, a three-dimensional thing, and so on. But sort of the notion is that out of these discrete nodes, there emerges something that's like ordinary space. And sort of everything has to be part of this. It's kind of actually, it's very similar to some of Einstein's later sort of ideas about how things might work, that sort of everything is just space. And all the matter and particles and things have to be features of space. They don't get to be something that sort of exists as a separate thing, not being part of space, so to speak. Well, so then the question is, so this is space. How do you update space, so to speak? And there's all kinds of issues about, there's all kinds of issues about how you think about time. Suffice it to say, you can look at lots of different kinds of rules for updating the universe, and many of them are clearly not our universe. Like the thing just freezes after 3 steps, not our universe, right? The thing expands in some trivial exponential way and is very regular, very homogeneous, not our universe. The thing is clearly, it's an infinite dimensional thing, clearly not our universe. And lots of other pathologies that can happen. But it turns out if you just start enumerating possible rules, lots of them, a surprising number, actually have the feature that they just blob around and they do very, very complicated things. Basically, anytime you can crack what they're doing, it's not our universe. Anytime you can say this is the Cayley graph, it's generating the Cayley graph of some group or something like that, not our universe. The cases where it's complicated, you can't tell. What's interesting is I've been able to figure out a certain amount from what you can tell. And so an example that I think is pretty neat is that you can derive certain features of space-time. So for instance, one of the things that happens is you can ask, like in fluid mechanics, right? You start from the molecules bouncing around underneath, and then you derive the fluid equations. And from looking at that molecular dynamics and taking certain limits and so on, you can derive with certain approximations the fluid equations. So the question is, when you just have this microscopic stuff going around, what kinds of things can you derive about the large-scale behavior? Okay, so the first big excitement is that you can, subject to certain conditions, you can derive special relativity, which is quite exciting because most theories have special relativity built in. In fact, every theory has special relativity built in. But in these systems, you can derive, the actual logical thing is, if there is a single thread of time in the universe, then it implies special relativity in these theories. Second thing you can do is you can actually derive the Einstein's equations for general relativity. And essentially they come about in more or less the same way that the fluid equations come about from molecular dynamics, although the situation is more complicated here because there are networks and it's a whole mathematical adventure, but you can derive that, so that's pretty interesting. And then you can start asking about quantum mechanics, and there are at least pretty good indications that you start seeing kind of quantum mechanical type phenomena. It's a slightly long story because the system looks deterministic, but there are basically what happens is that there are these all that matters, all that you can detect about the system is these so-called causal networks of how different events in the system affect other events. And the microscopic ways that the updating happens are independent, can happen in many different ways while having the same causal network. That combined with the fact that these systems are not in any fundamental sense like three-dimensional or any fixed dimensional allows one to avoid issues about violation of Bell's inequalities and all these kinds of technical things, and you can start getting the beginnings of seeing some interesting quantum mechanical and quantum field theoretic effects. So so the challenge there is can you it's a big sort of technology adventure to sort of recapitulate the history of physics and be able to say, okay, here's a candidate universe, go figure out its properties, and then say, well, how does it compare to the universe that we actually have discovered from all the existing work that's been done in physics? And that's a non-trivial thing, to go from the candidate universe to sort of deduce its effective physical laws and compare it with what we know. But that's what the project is, and I've been too distracted working on Wolfram Alpha and all kinds of interesting technology directions for the last few years to pursue this as much as I would like. But it's my longer-term goal to try and nail this down and find out either, it could be the case that our universe just isn't one of these simple universes in the computational universe of possible universes. But we don't know that yet. And it would be kind of embarrassing if it was there's a reasonable candidate at around number 1,014 maybe. And if that turns out to be right, it will be really embarrassing not to have nailed it down. Of course it could be completely not right, and it could be that our universe is out, very far out in the space of all possible universes, or maybe not describable in this kind of way at all. We don't know. And unfortunately, this computational irreducibility phenomenon really bites us, because it says, we have to, in order to know whether something is our universe, we better not have to run it for as long as our universe has been running. We better have some shortcut way of figuring out what's going on. So it's non-trivial to kind of, you have to be lucky to have enough computational reducibility to be able to compare these things properly. Yes?
The cellular automata that I've seen you mention have all been expressible in a two-dimensional plane. Are there higher dimensional ones too?
Yeah, sure. I mean, you can make cellular automata in any number of dimensions, and you can make. I wonder if I have an example here readily. How do you label them? Well, there are many more to have. So really, you just have to give. Well, okay. So here are some 2D ones that are just growing out. Those are single time slices of 2D ones. There's a fun one. That's one of my favorites. That's a 2D one on a square grid that grows an almost perfect circle. Completely deterministically grows an almost perfect circle. Actually, this is one that grows an almost perfect, I don't know what it is, some kind of vegetable-like thing. But these are, I mean, the rules. It's just, you just specify the rule. I mean, there are many more rules, so you don't get to, I mean, I have numbering schemes for them, but they're not quite as convenient as they are for the simple one-dimensional ones. Yes?
You give sort of dossier-like answers to questions, but I was wondering whether you could, if you have a very specific question, like who is the most famous person who was born in Springfield, Illinois, could you do that too?
Yeah. I mean, usually what happens, so what we found is that, okay, so this is let's see whether that works. I'm actually slightly pessimistic about that particular query. Let's see, most famous person born in Springfield, Illinois. As I say, I'm pessimistic about that particular question because I suspect that isn't a. Yeah, right. I mean, there's lots of. Okay, so that. Okay, so this just said it's using the closest interpretation it has, which is all the notable people it knows born in that city. So that wasn't a. Actually, if you see the version of Wolfram Alpha that Siri uses on the iPhone 4S, well, actually, that's a case where one is interested in getting sort of the straight single answer, because but that's a kind of a. But what we found in most use cases is that actually people really like having the whole report. That is, if you know, in a vast majority of cases, if you just say this is the answer is 42, for example, people, you know, that doesn't really satisfy people. But if you show it's 42, and here's where the 42 lies in some plot of all possible, you know, answers, and here's a bunch of other detail about it, then they are much happier. And in fact, I find that myself. You know, I see these things where we just get an answer. It's this, you know, and I'm like, do I really believe that? You know, what's really going on? So we haven't particularly emphasized giving the sort of single answer as opposed to giving a whole report. Although there are cases like the Siri case where it's relevant to try to identify something which, for example, in that case, you can read back in a short way.
You might be asking a sequence of questions, or each one depended on the previous one.
That's right.
You might want to, the specific answer to the first question might be the lead into the next.
That's right. So I mean, that's represented in this kind of interface by just, you know, you follow the link, so to speak, because that will be, you know, one of these will be a particular answer, whoever that is a particular answer, and then you follow that link and you get to the answer. Now, and so, you know, actually that's an interesting thing that we're actually working on, is this kind of thing where you can, you know, go from something and sort of chain down a sequence of answers. And there's sort of a question of how do you visually represent that, and actually we think we have a pretty good scheme for doing that. The case that I showed you of Wolfram alpha inside Mathematica is a case that works precisely like what you just described. Because, okay, so for us, a big sort of conceptual difference is in Mathematica, there's always just one answer. In Wolfram alpha, there's a report. Right? And so how do you merge those two things together? So there are cases in which, in Mathematica, you know, you can use Wolfram alpha to just get a single result, and then you can sort of chain it down as you would in a typical Mathematica session. And so there's the question of how do you take these much fuzzier results and chain them? And as I say, I think we have a good sort of human understandable way of doing that. But it's an active area of investigation. Yes?
How do you go ahead projecting things into the future? For example, there's a finite probability of a big earthquake here today, and if you ask Wolfram alpha about that, it might go back to USGS predictions, but you have other techniques for projecting data now into the future.
Not anything very interesting. I mean, we're starting to do some things. I mean, one thing that we've tried to do is to, that's just the earthquake feed for right now. You know, if you say something like, something like this, you know, you'll see, you know, it'll probably, okay, so it'll just give some, okay, that actually that didn't give me what I thought it would give me. Let me just see what happens if I just ask in general about Microsoft. So here, you know, I'll get some results, and then somewhere down here, probably, yeah, okay, so here, you know, here there are some projections. Okay, now these projections are made on the basis of a model that uses previous things, and these are sort of sample projections, and this tells me that, you know, 95% confidence interval for, you know, that it'll be between -12% and +13%, and so on. That's based on historical volatility, et cetera, et cetera, et cetera. You know, it's a pretty standard model in this case. The question of whether, you know, the question of other kinds of predictions, so like weather prediction, for example, okay, so we obviously get, you know, the standard weather predictions, and you know, everybody gets the same, you know, weather codes that get run, and they produce these ensembles of predictions, and then you have to parse out what you actually want to say the probability of rain is, given that, you know, 3 things said it would rain and 7 said it wouldn't, and, you know, et cetera, et cetera, et cetera. You know, we've looked at, for example, how you can improve those predictions by knowing what happened in the past. And actually, one of the things is that I have to say weather forecasters, I think, have gotten good in the following sense, that the errors are really quite Gaussian and random. That is, that they're wrong, they're often wrong, but you can't actually improve the predictions, so far as we can tell, by going back and looking at what happened with previous predictions and comparing those to what, you know, the actuality. But in general, I mean, this sort of question of what can you learn about the world, I mean, we were, for example, with these user data sets that people can upload, we can do things like compare those to, you know, somebody uploads a time series, something that we recognize as a time series. We can say, well, what is that time series correlated with? You know, is it correlated with, you know, the price of bananas or something, right? And because we probably have. Let's see whether we have something like that. Some totally random. Okay, so the average price in the U.S. of bananas is $0.59 per pound, and I wonder what that spike was. That was probably some revolution in some banana country. I don't know. But you could ask the question, if you look at some completely other thing, what is it correlated with? I have a feeling that's mostly going to be noise, but we will see. Yes.
Out of alpha that has truly surprised you in terms of answer?
I find surprising things all the time. I mean, well, like what we just saw here. I'm surprised that there's a single peak in the banana price. I don't know why that's the case. I mean, it's actually there's one of these that I think that one of the main things is that for me qualitatively, there are all these things where I kind of have the idea, well, there might be a way to compute that. It might be a known thing. It might not be. And in the past, I would never have bothered to go and track it down. And I'm about as computer-oriented as anybody, so to speak. And I'll if there's something where I think it can be figured out, I'll actually go and try and figure it out in many cases. But going from it's possible in principle to it's trivial to do it has had a big qualitative effect for me.
Well, sure. I mean, of course, there's things in the world that surprise you. I'm thinking more in terms of you have some mental model of alpha and what it should be able to do. Do you get answers that you look at and say, how did it do that?
Occasionally. I mean, it's still.
And what
it doesn't surprise me as much as it perhaps one day will, because what it's doing is, I mean, it's still staying fairly close to the ground in terms of there are algorithms that have been implemented, and it's going to apply those algorithms. It's sometimes, it's a little cleverer at figuring out, there's this chain of things that it can work out, and so it gets to an answer.
That's what I'm asking.
Yeah, right. No, I think that one of the surprises that I've had is a little bit of a different kind of surprise, is what ends up being computable in the world. Right, so what types of things you can actually make computable. So for instance, I'm thinking, a Shakespeare play, for example. Okay, what is computable about a Shakespeare play? Right, you might have thought there's nothing. Okay, but it turns out, you can go in and you can chop it up and you can say how many words it has in it and so on. You can say, and so on. But then you can actually also work out, okay, which character was speaking when in the play and so on, and that's not difficult to do, and you can work out all kinds of things, which I've been surprised by. If I'm going to go on for it, does anybody happen to have a MacBook Air power cable? Could I borrow one, please? Okay. Thank you very much. Is that going to work from? No, that's not a MacBook Air. That's a generic MacBook. Okay. Thank you very much. Just remember to get it back from me. It's so. Yes. No. It's just a minute. Let me see. What can I unplug here? Oh my. There we go. And now. That didn't work. Oh, come on. That worked. Thank you. Anyway, so I think one of the things that has been surprising to me is the things that end up being computable, that end up just being computable about the world that I hadn't expected to be. I would say in terms of yeah, it's probably the most obvious. I mean, I'm trying to think. I mean, there are all kinds of decisions that I would have that I made differently because I was actually able to compute something, and that I would have made differently at other times in my life if I had been able to compute something immediately. But I think those are the kinds of things that come to mind immediately. Yes?
You've talked about you studying the queries that come in. is that available for other people to look at too, or to do any statistical analysis of the queries?
Well, I think there's we kind of say we're going to keep all queries private, so we're not going to give anybody a big lump of query data.
Well, but indeed, some of the other websites do give some kind of data on such queries.
Yeah, we might do that at some point. I mean, it's kind of interesting sometimes. You can see, you can see stuff about what's happening in the world by people, things that people are making queries about and so on. I don't know. Yeah, I mean, I think right now we are. What ends up happening is it's lots of. We get these query streams and then we carve them up, and we're doing a bunch of analysis on them. I'm sure eventually there'll be academic papers and things about them. But right now we're just busily trying to do as much analysis as we can to try and make Wolfram Alpha do things that people want, as effectively as possible. Yes.
You mentioned that you get special data feeds like from the FAA. Do you have to pay for some of these feeds?
Of course.
People give you trouble?
I mean, yeah. I mean, there's endless things. I mean, like for example, okay, airplanes. The U.S. Well, the FAA is FAA has all kinds of issues, but that one is at least a feed you can get. In Europe, for example, Eurocontrol, which is the analog of the FAA, is a more complicated thing. They're very helpful, but they say, but it doesn't work like the US. There isn't a constitution that says government by the people for the people, so to speak. There's no requirement of having the data be available and so on. So it's more complicated, right? And that's true for. This is it's a complicated, time-consuming, sometimes expensive thing to piece together all these different kinds of data about the world, and I think that's that's one of the things that we're spending lots of effort on, and as a company we're trying to sort of make work as well as we can. Yes.
You mentioned your computational document format.
Yes.
And can you talk a little bit about your goals for that and how you see that fitting into kind of our current world of PDFs and tech documents and things like this?
Sure. Well, let's see. I can just show you. So I mean, the obvious kind of there are a bunch of obvious use cases. So for instance, let's say you're writing some report on you have some. This is, I think, a real one. This was some person who was doing some report to the Texas state legislature, okay? And in this report was this computable thing. So there's some model for something to do with insurance. And right there inside the report, it's computable. And you can move sliders around and you can find out what happens if you change some parameter of some model. So that's an example of a type of thing you can do. And so the idea is that you can, the two use cases that have emerged quickly are textbooks and reports, basically. Textbooks, there's a calculus book that just came out that has lots of essentially algorithmic diagrams in it. Then for reports, like within our company, for example, within our company, there's all of our sort of internal reporting is done in CDF, and it's actually really nice because you can take some report, you can drill down, the thing can, within the report it can go out and access some database and go and suck in more data and so on. So it's really taking what is, what one first of all thought of as a document and turning it into something that's actually computing things. Should wrap up in a minute, so maybe one or two more questions and then we should wrap up. Yes? Please.
How many domains do you have, and what was like your priority in trying to get those?
Well, so we have, I don't know how to count domains exactly, but you can look at just examples here. That's some indication of domains. I mean, there are thousands of these things, but I don't know, we don't really have a way to say this is a domain and this isn't a domain. Like, are bolts and nuts different domains, or are they the same domain? In terms of priority, we actually, so we started off with some of the more hard science kinds of things because they were very, it was very definite what you could do there. We've kind of moved out to the more sort of culture-oriented things, and we actually just started to have a big push into sort of everyday consumerish kinds of things. So, we just started with sports stuff recently with NFL data. We're going to have a bunch of things in much more consumer. We did, you can do things like you can say something like, you could say something like smartphones, and you'll get a bunch of information about the world of smartphones based in this particular case on the right now on the Best Buy catalog, and so you can compute all kinds of things there. There are some price distributions and things like that for smartphones and so on. I think generally, we've been moving from the more hard stuff to the more consumer stuff, and in terms of priority, it's really easy for us in a sense because we get a giant to-do list every day. It's there are all these feedbacks, there are all these things that work, there are things that don't work. The current length of the to-do list is about at the rate we're going to absolutely finish the to-do list will take about 20 years. Which is not that scary to me. I've been working on Mathematica for 25 years, but it will actually take a lot less than that. And what you get by the time you're, as you're in the tail of that, it's pretty obscure. And actually, the to-do list has not changed that much in the sense that we know what the domains are that people want. Now, probably one thing that has happened is that people's expectations and our own expectations for what we can do have gone up and up. So a domain used to be, well, you just put in some basic things, but now it's, well, you've got to generate these very elaborate reports, you've got to be able to link it up with all sorts of other things, you've got to be able to, sort of look at things across different domains and so on. So expectations have gone up, so that makes it more difficult. But yeah, yes.
So you've been mentioning simulations a lot in your work, and today when scientists do simulations, they use compiled languages because they're fast, like C and Fortran. Do you think Mathematica, with its holistic modular structure, will be able to reach the efficiency and performance of those languages, and will it maybe even make writing simulations easier for future?
Well, lots and lots and lots of people in the world use Mathematica to do simulations. And the typical thing is that, when you think about doing a computation, there are these sort of lumps of computational work that have to be done. So one lump might be work out the eigenvalues of a matrix or something. Once you're working out the eigenvalues of a matrix, I will be shocked if Mathematica is not as fast as it could possibly be at doing that. And if you wrote your own custom program for doing it, it will be slower. With certainty, I would say. So the issue is, are these lumps of computational work, do they map correctly onto what people want to do in simulations? And, basically what we found right now is that for most kinds of things people want to do, okay, if they write good Mathematica code, it will be very fast. If they write Mathematica code that looks like Fortran, it will be kind of lousy and slow. Now, actually, we think we have a solution to that, which is to rewrite the code for them. That requires doing things that are like what we do in Wolfram Alpha, and basically doing linguistic understanding, not of natural language queries, but of code. And we have a bunch of projects working on things like that. And that we think is the best solution, because if you can turn their, their do loop into some, functional programming nest thingy, we can make it really, really fast. It's kind of painful for us to make a do loop. I mean, actually, in Mathematica, in the latest versions of Mathematica, we have code generation. So you can do, for things which can be reasonably moved into C code, for example, we can generate the C code and compile it and so on. But clearly, a lot of what Mathematica does cannot be just turned into small lumps of C code. So, that's the, I certainly would hope that it's sort of a trajectory that we're on, and it's certainly true in the world today that lots of people use Mathematica for simulation, and there are plenty of places where it's used in real-time loops and all this kind of thing. So I think it's, I think the main thing to realize is that if you can identify the lumps of computational, operation well, then you're going to come out way ahead relative to using sort of a one-step-at-a-time, compiled language where will have gone to nearly as much effort to optimize how those lumps of work operate. Yes?
What language is Mathematica written?
Most of Mathematica is now written in Mathematica. So, I mean, there's a C code, there's lumps of C code, there's other kinds of, there's Java, there's all kinds of languages inside the raw source code of Mathematica, but the vast majority of the code is now written in Mathematica. Yeah?
You said that a lot of the intelligence can be computed. So do you think there's any rules of the cellular automata that are
related to that?
Well, so I mean, the thing that I've kind of realized is that these things that one does that sort of are intelligence-like ends up being, I mean, it's kind of the long story of AI, that the things that kind of seemed like they'd need that spark of human intelligence, there's just an algorithm for doing it. And that's really what we're finding. And I don't know what, I look at, work that's been done in AI and so on, and all this effort that's been put in, and say, there's this really cool example that does this and this and this. I say, surely we must be able to use all this work that's been done in this direction. And it's like, well, there's this really cool example, but it's just some very isolated, obscure thing. And it's like, there's this cool example, but if you actually say, let's systematically try to, let's say there's some cool example about how, I don't know, you can deduce from the fact that somebody is, president of the US, that they're this, that they're that. Well, okay, that's great. But, what about, the whole database of all the world leaders throughout history and so on? That's what you really need to actually be able to answer typical interesting questions. And that's sort of a very different problem from the, let's make a cute string of inferences and so on. So I should probably wrap up because I have to run off somewhere else. But thank you all very much.
For more, please visit us at stanford.edu.